Hey everyone, welcome back. So today's video starts with a very simple question, and one that you probably have to answer a couple times, especially if you do online shopping. So let's say you're on some online shopping site like Amazon, and you have two products in front of you, and all else held equal. Would you rather buy the product that has 100 reviews, so 100 ratings from other customers, and its average rating is 4.1 stars out of 5? Or would you buy the other product who has 1,000 reviews, and the average rating is 4 stars? Now, it's not an obvious question. I think maybe some of you have an obvious answer, but let me just talk you through the kind of trade-offs. On the one hand, the 100 reviews one doesn't have a lot of reviews, so we're kind of not as trustworthy of that 4.1 average, but it is higher, that average is higher than the 4 stars, but the 4 stars review has 1,000 reviews behind it, so maybe that's more trustworthy. So there's this kind of trade-off going on. Now, hold that answer in your head, and now answer this next question. Let's say we changed it so that now we have one product with 1,000 reviews and 4.1 stars, and the other product has 10,000 reviews and the average rating is 4 stars. Does that change your answer at all? So keep these answers in your head, and let's look through a statistical analysis of how to answer this in a more robust fashion. Alright, so I've written a little bit of code here. I'll make this notebook available to you, but it's not as complicated as some of the other notebooks, the Code with Me's we've done in the past. So what we're going to do here is we're going to basically do a Monte Carlo simulation. I think that's the most straightforward, most intuitive way to go about this problem. And we're going to look at the two products. So we're going to assume there's one product which has 100 reviews and the average rating is 4.1 stars. And we'll look at another product who has 1,000 reviews and the average rating is 4 stars. So the story begins with this first product, and let's say this is the distribution of ratings that we see on Amazon. So as a reminder, this product has 100 ratings and is equal to 100. And there's 5 different ratings you can give from 1 to 5 stars. Let's say that 5% of the people think it's 1 stars, 5% 2 stars, 5% 3 stars. We have 45% think it's 4 stars, and we have 40% think it's 5 stars. And if you take the average of all of this stuff, it ends up being 4.1 stars. So this is the distribution for this product. Now, what we're going to do, we're going to assume this is the true distribution for the population. That is an assumption we'll come back to at the end of this video, but for now, for this analysis, we're going to assume this is the distribution of people who would review this product. And then what we're going to do is we're going to do a bunch of Monte Carlo runs. So each Monte Carlo run goes like this. We are going to sample 100 people from this distribution. So we're going to take those 100 people's reviews that we've sampled from this distribution and take their average. And that's the first Monte Carlo run. Then the next Monte Carlo run, we're going to just independently, randomly sample a new 100 people from this ratings population, take the average there. And we do that many, many, many times. And that's what a lot of the code here is doing. I won't walk you through the code too much. I'll leave some comments later when I post it. And this is the distribution that we get. So to make sure we're all on the same page, I did many, many Monte Carlo runs, and in each one I took 100 samples from this distribution of ratings, so 100 people, and took their average. And so what you're seeing on the x-axis here is all those averages of those 100 people, and the y-axis is the density. So this is a distribution of those average ratings if the sample size was equal to 100. And we see that the center of this distribution, the average of this distribution, is 4.1, as we already suspected. But the standard deviation is 0.1. So in kind of general terms, what we could say is that the average rating we're seeing on this site is 4.1. But if we go plus or minus 1 standard deviation, then that's plus or minus 0.1 rating points. So that's what these red bars here represent. So it's kind of a general statement you can make is that the average rating loosely might lie between 4 stars and 4.2 stars if we're talking plus or minus 1 standard deviation. Now let's do the exact same analysis, except for the other product, who has 1,000 reviews, and it has an average rating of 4 stars. We're going to assume the distribution looks like this, which is sort of similar to the distribution we looked at before, but the 4-star ratings are relatively higher than the 5-star proportion here, which is what makes the average rating here equal to 4 stars instead of 4.1 stars. Now we do the exact same thing, and the only difference is that in each Monte Carlo run, we take 1,000 samples from this distribution instead of 100. And then for the next Monte Carlo run, we take another 1,000 samples from this distribution and take their average rating. When we do that for many, many Monte Carlo simulations, the same number of Monte Carlo simulations as we did for the previous product, we get this distribution of average ratings. So as suspected, the average is 4 stars, so it's centered at 4 stars. But the biggest thing to note is that while this distribution had a standard deviation of 0.1 stars, this has a standard deviation of a third of that, 0.03 stars. And that means we can make the general statement that the ratings for this product loosely lie between 3.97 and 4.03 stars, so it's a much tighter range. To see this tighter range, let's plot the previous distribution and this distribution on the same plot, and we get this plot here. So the blue curve you're seeing, the fatter curve you're seeing here, is for 100, that product with 100 ratings, and this orange or red curve here that you're seeing is the product distribution for 1,000 ratings. And now you can start making a better understanding about which product should I buy. For example, this blue curve does have a larger standard deviation, but it does generally seem to be ahead of the red curve. And the red curve is definitely more precise, but it does, for the most part, seem to be behind this blue curve. Another look that we can do is we did the same number of Monte Carlo runs for the small sample size of 100 and the large sample size of 1,000. So what we can do is just take the difference between the average rating for each pair of runs if we line the runs up one by one. And that's the difference distribution you're seeing here. So I know that there's a lot of moving parts here, so let's kind of make sure we understand what we're looking at. If I took the difference between the small samples average rating and the large samples average rating for each pair of Monte Carlo runs, then it's going to be this distribution here. And you see 0 is right here, and 82% of this distribution lies above 0. Another more intuitive way of saying that is that 82% of the time, the small sample's average rating is actually going to be above the large sample average rating if the distributions were the exact distributions that we looked at the beginning of this video. So personally, based on all this information, I would probably buy the product that has 100 reviews but has 4.1 stars if the only criteria I was going off this point was the average rating. So there's still room for kind of argument there, because you could say there's an 18% chance that you're making the wrong decision here, and that's not small. I mean, it's 18%, and you'd be correct. So this kind of becomes a judgment call at this point. But now, since we have this whole framework set up, let's just play with the numbers a little bit. So let's say that we look at that second question from the PowerPoint. Let's say that the small sample now has 1,000. So let's run that guy. And let's say the large sample now has 10,000 ratings. So let's run that guy and regenerate all of our plots. Before I show you the answers, think about how these plots might change. What is your suspicion? And then we'll look at these plots together. So we see that for the first one, the standard deviation is now 0.03. For the second one here, the standard deviation is much smaller now. It's 0.01. So we have a very precise range. If we look at these two things together, they look like this. So now the story has changed a lot. Now there's a lot less room for argument between different people. Clearly, this blue distribution with 1,000 samples is pretty much always ahead of this red distribution with 10,000 samples. And what's happened here intuitively is that instead of looking at sample sizes of 100 and 1,000, which do leave a little bit of room for error, now we're looking at sample sizes of 1,000 and 10,000, which are both precise enough that the average rating we're seeing is a good indicator of whether the product is actually better than the other product. And if you look at the difference distribution, we see that all of the differences, almost all of them, lie ahead of 0. So we're pretty confident in picking the product that has 4.1 stars. So let's just do one more. What if instead of fudging with the sample sizes, so let me put these sample sizes back to 100 and 1,000, and instead let me fudge with the distribution of ratings so they're closer to each other. So I'll set this to 0.5, and I'll set this to 0.35. Does that add up to 100%? 35, 40, yeah, that adds up to 100%. So what I'm doing right here is that I fudge with the distribution for the small sample a little bit, so that now instead of having 4.1 average stars, it has 4.05 average stars. So I've moved its average closer to the average for the large sample size, which remains as 4 stars. So to be clear, now we're comparing two products. One product has 4.05 average stars, but 100 reviews. The other product has 4 stars, but 1,000 reviews. So it has just a little bit less average rating, but a lot more reviews behind it. Let's look at how these plots change. So the distributions now are less separate and more on top of each other, so it's a little bit harder to tell. And if we look at this one here, it says that only about 69% of the time would the small samples average actually be above the large samples average. Remember, the very first run we did, this number was 82%, so now it becomes a lot less certain which one we should pick. So this kind of certainty about which product you should pick depends not only on the difference in sample sizes, but also how close together the average ratings are. So obviously, when you buy your next product on Amazon, I want you to fire up the Jupyter Notebook and write the custom Python code to figure out which product you should buy. And that is the takeaway from this video. So the big kind of assumption I made in this video, and I want to be very clear that this is not always going to be true, is that I took this distribution from these 100 people that we see and treated that as the population distribution. Obviously, when the sample size is small, like 100, that's not going to be very correct. If your sample size starts increasing, you have more confidence that the distribution you're seeing is close to the population distribution. But with small sample sizes, you might want to do a little bit more sophisticated statistics. But this is a good starting point, kind of just saying that, okay, I get this distribution, let's go off of that. So hopefully you like this video. If you did, please like and subscribe for more just like this. I'll catch you next time.